Welcome learners in the series of videos on topology. We are looking at countability properties and to be precise, first countable species. In the previous two videos, we have seen that the subspace of first countable space is first countable and the product of two first countable spaces is first countable. Okay. Now in this video, let us show that the continuous open image of first countable space is first countable. So let us take that as theorem. Continuous open image of first countable space is first countable. Okay. That means we have two topological spaces x and y. So let me just draw the diagram for simplicity. Let us take this to be our first space x, and this side we have another topological space, say y, and we have a function f from x to y. This is your function f from x to y, which is continuous function and which is open also. Okay, so let's begin. Proof. So let us take two topological spaces first, x and y. So let x and y be two topological spaces which are first countable. So x and y be first countable spaces. Okay. Now no, I should not use x and y be the first countable spaces. Rather, let me take this to be topological spaces, because we need to show that the image of first countable space is first countable. So let x and y be two topological spaces. Okay, and let us say that this x is first countable. Let x be first countable. Okay, we need to show that. Let us take the function as well, right? And let f from x to y be continuous open map. Open map means it will take a open set in the domain to open set in codomain. Okay, so let us show that fx, the continuous image of this the domain, that is fx, is first countable. Okay, so claim fx is first countable, right? We need to show that fx is first countable. So let us take a point in fx. Let x belongs to fx. Okay, let us use y, standard one. It is in the codomain, so let us take y in fx. So we have, say, fx here, somewhere here. If it is surjective, it will be whole of y. So this is our fx, and we have taken a point y in fx. So we have a point y in fx. So let us take a point y in fx. So since y belongs to fx, and this implies This implies there is a point in the space X, there exists some X in X, there exists some X belonging to X, such that this X is mapped to Y, such that fx belongs to, fx is equals to Y. Fx equals to Y. That means we have a point in the domain which is mapped to this Y. So let us take that point to be here. We have this X which will be mapped to Y, that's fx equals to Y. Okay. Now we have this X in X. Now since this X belongs to X, and we also by hypothesis we know that and X is first countable space, first countable space, right? That means there exists a neighborhood basis for this X, right? This implies there exists say neighborhood basis Bn, n belongs to natural number, right? That is neighborhood basis of X in X. Now from this basis, neighborhood basis of this X, we will get the neighborhood basis for fx. So you can see what will be that neighborhood basis for fx, that is Y. Okay, so let us claim that images of this. Claim let us take the images, that is f of Bn such that n is in natural number is neighborhood basis of fx, that is Y in fx. Of course, if this is a surjective function, then fx is equals to Y, so in Y. Okay, so now to show this, let us take a neighborhood of Y in fx. Okay, so of course we know that these are open because f is open map, so it will take it is open map which is continuous also, so it will take a open map to open maps. Okay, so let us show that there exists some if you take a neighborhood of any neighborhood of Y, so let us take that first. So let us take say U be neighborhood of Y in fx. So we need to get one element of this form such that this f at Bn will be inside U. Now since U is neighborhood of fx, we know that this U is open and f is continuous. So since f is continuous, we know that this implies inverse image of this open set will be open. So f inverse of U is open in the domain X because f is continuous function, and we know that this, where is it here? We know that this is the basis for X. Okay, since X is first countable, we have this basis, and f inverse of U is open in X such that this X will be in f inverse of U. So this implies, let us not write all, this implies there exists some n naught in N such that this X right here, this X belongs to f inverse of U, and this is open. So there exists some n naught in N such that this X belongs to Bn naught which contain inside U by definition of first countability, and this is the neighborhood basis. So this implies since X belongs to Bn naught which contain inside U, this implies this fx. What is fx? Fx is nothing but Y. So Y is equals to fx belongs to f at Bn naught, and that will be contained inside f at U. Okay, so we have got a neighborhood u of y, we found an element of this form from this set such that this y belongs to f at b and not, and that contains inside u. Right? Sorry, I think I made error. There exists and not in n such that x belongs to b and not, which contains inside this set f inverse of u, not f u, f inverse of u, and this will be f of f inverse of u will be u contained inside. So again, you can check any other mistakes if we have done. So we have got a neighborhood f at b and not which contains inside u, and therefore we can say that hence fx, that is the continuous image of open set fx, is first countable. Okay, so continuous open image, again remember why we have used open, because we have a set of open sets in our domain, and since we are claiming this is the neighborhood basis, we should claim that this is also open in y, and since f is open, there is open map, we can claim that f at bn is open in fx. Okay. So that is all about the proof of the statement which says continuous open image of first countable space is first countable. Okay, this is how we have started. We have fx, then we have a neighborhood of y, that is u, then since it's ulta, we have a neighborhood of this, that is f inverse of u, and we have the collection of the sets which contain inside. So this will have b and not, and this b and not will go here, and it will be f at b and not inside. So this is all about the continuous open image of first countable space is first countable. Now in the next video we will talk about the second countable spaces. So stay tuned and see you in the next video.